Have you ever wondered how winemakers know the exact moment when a grape is ready to become wine? The grape harvest is one of the most important stages in wine production because the quality of the grapes directly influences the flavor, aroma, and overall characteristic of the final product. However, determining if the grapes are ready to become harvested usually requires manual inspection and the experience of vineyard workers. For this reason, we developed an automated prototype using Lego Spikes Prime, capable of identifying grape grabs through color and distance sensors. In our simulation, the color sensor detects magenta-colored grapes, while the distance sensor verifies whether they met the programming maturity condition. When both requirements are satisfied, the system automatically approves the grape for harvesting. The purpose of this project is to demonstrate how automatization can support agricultural process, improve efficiency, and reduce dependence on manual inspection. Additionally, it shows how technologies such as sensors, actuators, and programming can be applied to real-world problems in viticulture.
The idea was to show how automation can help make the selection of grapes faster and more accurate before wine production. To do this, we used three control variables. The first one was grape color, obviously. The color sensor checked if the grape was magenta, with in our prototype represent a ripe grape ready for harvest. The second variable was distance. Using the distance sensor, the system checked if the object was 15 centimeters away or less. This was used as a simple way to represent grape size and maturity. Finally, the system made a decision if the grape was magenta and the distance condition was met. The system accepted. If not, it was rejected. In this way, the prototype simulated an automatic inspection process that could support grape harvesting.
Starting from the original Lego Spike Prime color detector model, we made several modifications to add into our project requirements. The most important change was integrating the color sensor and the distance sensor into the same inspection point, allowing both to work together and improve the detection process. We also removed the decorative pieces from the original design to make a structure lighter and more functional. In addition, the prototype was adapted to the simulated automated grape classification system, where the model performs the sorting movement based on the information received from the sensor.
First, we test the prototype using an object that doesn't have the required color. As we can see, the system doesn't respond because the object doesn't meet the programmed conditions. Next, we use a magenta object, but we place it outside the accepted distance range. Even though the color is correct, the system doesn't approve the object because the distance condition isn't satisfied. Finally, we place a magenta object within the required distance. Now both conditions are satisfied and the prototype automatically executes the program response. As shown, the model performs a yes movement, indicating that the grape has been approved and can continue to the next stage of the process. This demonstration shows how the prototype can make automatic decisions based on predefined criteria, simulating a simple grape selection process during harvesting.
After implementing and testing the Lego Spike Prime prototype, we were able to verify that the system correctly identified grapes that met the program maturity conditions. In our simulation, magenta-colored objects represented grapes that were on an optimal state. The color sensor successfully detected these grapes, different from objects with other colors, which were automatically rejected by the system. Additionally, the distance sensor was programmed with a threshold of 15 centimeters. Only when an object was detected within this range and the correct color was identified, the system approved the grape. These results demonstrate that the prototype can perform a fast, objective, and consistent classification process. By automating the evaluation criteria, the system reduces the possibility of human mistakes and ensures that only grapes meeting the established conditions move forward in the harvesting process. Furthermore, the project showed the potential for incorporating additional sensors capable of measuring variables such as temperature, humidity, grape health, and even sugar content. This would allow future versions of the system to make more accurate and comprehensive harvesting decisions. Although our prototype was developed as an educational model, its operating principle can be applied to real vineyards. An industrial version could use sensors and cameras distributed throughout the vineyard to monitor variables such as grape color, size, temperature, and humidity. When the system detects that the grapes have reached the desired maturity level, it could automatically notify vineyard operators. This would help reduce inspection time, improve harvesting decisions, and increase the consistency and quality of wine production. Rather than replacing workers, the system would provide valuable information to support the decision-making process. In conclusion, this project demonstrated that automation principles can be successfully applied to grape harvesting using sensors, programming logic, and automated decision-making systems. The prototype effectively simulated the harvesting inspection process by combining color and distance detection, proving that sensor-based technologies can support agriculture operations. Finally, our results suggest that the future developments incorporating advanced sensors, computer vision, and environmental monitoring technologies could significantly improve the production of higher quality wine. Thank you very much for your attention.